In this video, we're going to take a look at how to name and draw alkenes. So we're still exploring aliphatic hydrocarbons. In the last few videos, you saw aliphatic hydrocarbons that were called alkanes. They only had a single bond. Now we're focusing on alkenes, which have a double bond. And then in the next video after that, we're going to take a look at alkynes, which have triple bonds. So right now our focus is on hydrocarbons with carbon-carbon double bonds. So alkenes, hydrocarbons with at least one carbon-carbon double bond, and they're considered unsaturated hydrocarbons because they don't only have single bonds, so they don't have the maximum number of hydrogens that could be bonded to that hydrocarbon. The general formula for an alkene is CnH2n. That's for a straight linear chain with branches as well. It doesn't really matter. And if it's for cyclic, you have CnH2n minus 2 because when you make that ring, you have to take off 2 more hydrogens per unit. Since you need to make more connections for the carbon. So how do we name alkenes? Well, this is a list of rules over here. It's very similar to naming alkanes, but there's a new rule introduced, and that's the priority rule. So essentially, your parent chain, when you try to find it, it does need to be the longest chain, but it has to be the longest chain that contains the double bond. And your double bond actually has priority. You want to try to number your parent chain such that you give it the lowest number possible. So if you have a choice, for example, to give the double bond the lowest number possible or the alkyl group or the halogen substituent, you really want to go the direction that will give your double bond the lowest number possible. Ideally, everything gets a low number, but if there's sort of a tie, the double bond wins every time over the alkyl group or the halogen. And then the other thing that kind of changes as well when you're naming your alkene-based hydrocarbon is you have to change the ending. So the ending will have ENE, and you also have to indicate the position of your double bond because the double bond may not be a carbon number 1. It could be a carbon number 2, 3, 4, or 5. It doesn't really matter. So what you do is in the middle, you put the number to indicate your where your double bond is. Sometimes you might have multiple double bonds. If you do have that, you'll kind of name it as you see here. So you'll name your molecule as you typically would. You'll leave the A over here, so you won't drop the A. You'll put the numbers that represent where your double bonds are, and then you'll choose a prefix that shows you how many double bonds you have. So if there's 2, you'd put di and then ene. And we'll see more examples of that as we do the practice in the table below. So let's start with naming. First, we're going to identify our parent chain. And so there's only really one chain here, and this is it right here. And so we have to see how many carbons are in there. There's 1, 2, 3, 4, 5 carbons. So what that means is that we're dealing with a pent type of molecule. But we know it's not a pentane molecule because there's a double bond here. Now, where's the double bond located? Well, we have to start counting to number that to get the smallest possible number for the double bond location. And so you could count from the right side to get 1, 2, 3, 4, 5, 5 for carbon. If you count from the right side, your double bond would be at carbon number 4. It's basically the first carbon that you encounter with touching the double bond. Okay, but if you count from the left side, 1, 2, 3, 4, 5, your double bond is at carbon number 1. So what we have here is a pent 1-ene. You could have also written pentene because when you have a double bond at carbon number 1, you don't have to write down that position since it would be implied. It's almost like when you write H2O, you don't write H2O1, you just write H2O, and that one is implied. So we have pent-1-ene or pentene. I accept either one. For someone who's just starting, it might be a good idea to include your ones in there just so you get into the habit of remembering to put the position of the double bond whenever you're naming or drawing in other situations. So let's go ahead and try another example, but this time we're going to draw one out from a name. So we have 2-methyl hept-3-ene. Nothing is really different there. You start off by drawing your parent chain length. So it's hept. That means 7. So 1, 2, 3, 4, 5, 6, 7. And you can count from any direction that you want. I'll start from left and go to right. I want my double bond to be at position number 3. So 1, 2, 3. That's the first carbon that hits the double bond. And then my methyl group is at carbon number 2. So right here, CH3. And I get, so H3 over here. This has 1 bond, 2 bonds, 3 bonds. So we need just an H. This carbon has 1, 2, 3 bonds. So also just an H. This carbon here has 1, 2, 3 bonds. So also just an H. And this one needs H2, H2, and then finally H3. And so that would be our 2-methylhept-3-ene. You could have also drawn it out as a line diagram. Similar situation, just do your 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. At carbon number 3, 1, 2, 3. That's where we have our double bond. And at carbon number 2, 1, 2, that's where we have the methyl group. And there's the same molecule, just drawn as a bond line diagram. All right. So that was 2 examples done together. You can pause the video and try the next few examples yourself. And then you can unpause and check your work. So if you've tried the next examples, you're ready to now check your work. The tricky part here is a lot of students would have chosen this as their parent chain because it's the longest chain there. That makes sense. However, if you look carefully, you'll notice that you don't have an alkane anymore. You have an alkene. So that means that the parent chain is the longest chain that contains the double bond. So the longest chain with the double bond in it would happen to be this one over here. So that would be your longest chain. You have a 1, 2, 3, 4, 5, 6 carbon chain. It's a hex carbon chain. And you want to start counting in such a way to minimize the number on the carbon that has the double bonds. And if you can, also minimize your substituent numbers, but double bonds take priority. So you'll notice that counting from this area automatically gives you pretty small numbers for everything. If you went from the other direction, you'd get higher numbers. So we have a substituent over here at carbon number 2. So that's 2-ethyl. And then the carbon that contains the double bond is carbon number 1. So that's going to be hexene or hex-1-ene. And there is our name for our organic molecule. Try the next one, pause, then unpause and check your work. This one is an interesting one because it has multiple double bonds. So the straightforward thing about this is that your parent chain has to have all those double bonds in it. So it's got to be this whole thing over here. And so that would make this a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbon chain. That's a dec carbon chain. We also have some methyl groups here, so 3 methyl groups. So we definitely got some trimethyl happening here. And we got to start counting in a way to give us the smallest number for our double bonds and also our substituents, but focus on double bonds first to get as small numbers as you can. So you'll notice that this is pretty straightforward because you have a double bond on carbon number 1 over here. And so we could go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we can go the other way and do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And really, when it comes to a double bond, again, same idea. If you did green, you'd have your first one double bond at 1. But if you did red, you'd have your first double bond at 3. So we know that the green one is the one that's going to win, not the red one. So counting from left to right or right to left will be the winner in this situation here. So if we do that, we have a methyl at carbon number 4, at carbon number 5, and at carbon number, so 1, 2, 3, 4, 5, 6, 7, 8, sorry, carbon number 8 and carbon number 9. So we have 4, 8, 9. Oops, that's a comma. 4, 8, 9. Trimethyl. Then deca, because we have multiple double bonds. You have to leave the A there. Then we're going to put the locations of the double bond. We got one at carbon number 1, one at carbon number 4. So 1, 4, and then so 5, 6, 7. 7 deca triene. And that would be your name for that molecule, 489 trimethyl deca 147 triene. So now the next one is a drawing example. So let's go ahead and try that out. Technically, that's not a hydrocarbon because there's something more nitrogen in it. There's a bromo in it and a chloro in it. It's no big deal. We're still going to try it out. Very similar naming rules. You just have to know that bromo is bromine and chloro is chlorine. So we have a penta 2,3-diene. That means we have a 5-carbon chain. 1, 2, 3, 4, 5. And in that 5-carbon chain, we have a double bond at carbon number 2 and 3. So this is carbon number 1, 2, 3. So here and here. And also, okay, so our bromine is at carbon number 2, Br. And our chlorine is at carbon number 4. So 4 and 5. It's like this. And so now we just have to go and plug in our H's. So H3. This already has 4, so we're good. This one has 4, so we're good. This one has 4, so we're good. And then H3. And so this is 2-bromo, 4-chloro, penta 2,3-diene. You could have started counting from this direction if you want to, if you were naming this 1, 2, 3, 4, 5. And if you did that, you would have had something like this. You would have had 4-bromo, then 2-chloro, and then penta 2,3-diene. So it would have been essentially the same except for the positions of your bromine and chlorine. The double bonds are tied in this case. There's nothing different there. So you had to decide, well, what's better to go, left or right? And if the only difference is 4 for bromine, 2 for chlorine, what's the better system here? Well, the tiebreaker was alphabetical order. So that's why we chose to go this direction with counting, because our bromine would have had a smaller number compared to the chlorine. So really our priority was first trying to get the double bonds as low as they can. If the double bonds are tied, it doesn't matter what way to go. Next, you want to start looking at your substituents. You want to try to see like the smallest number at the first point of difference. But if they're tied there, then the next tiebreaker is going to be alphabetical order. So alphabetical order is kind of like your last case, your last ditch effort to try to get the priority done straight. Okay, so it is important, but it's not the first line. Okay, so now you can try this problem out over here. So we know we have a parent chain over here, 6 carbons long with a double bond. So we know it's a hexene, but a cyclohexene molecule. And we have to decide where to start counting. There's a couple ways you can do it. You can go 1, 2, 3, 4, 5, 6. Or you can go 1, 2, 3, 4, 5, 6. If you go the green direction, your methyl gets a 6. That's very high. So you're better off going the red direction for your methyl to get a 3. When you're counting, you have to go through the double bond. You can't, for example, you cannot do this. You can't go, okay, 1, 2, 3, 4, 5, and 6. You can't do that. You have to go through it. So you have to plan with going through it, not going around and meeting at the other end. So blue is not a valid way to count. So our best option was the red counting. So that means we have a 3-methyl, and then a cyclohexene, 1-ene. And that would be our name for this molecule over here. Let's try one more together. I'll draw one out, and then you can name it. All right. So this is our molecule. I'd like you to pause the video and try naming it. So hopefully you've tried it out. If you tried to name this, there's a few different ways you can go. You would need to find your parent chain first. So you could go, this is your parent chain over here. And I think that makes the best choice because it's the longest one that contains a double bond. You have to decide how to start numbering. You'll notice you kind of get a tie between the substituent here and the double bond here. They're both twos depending on which direction you start counting, but don't forget double bond gets the priority. So you're going to go with counting from this way, 1, 2, 3, 4, 5, and 6. So what do we have? Well, we have a 3-ethyl, 5-methyl, and then we have, this is a 6-carbon, so hex, and the double bonds at 2, 2, ene. And this would be our alkene name for this molecule drawn over here. So now you've seen a variety of examples for naming and drawing alkenes. You're encouraged to try more practice problems. The more you do, the more mistakes you'll make, and the more you'll know where not to make mistakes. In the next video, we're going to try to name and draw alkynes, which are very similar, except they contain a triple bond and end in -ine. So notice all the rules are extremely similar to each other, just some minor tweaks here and there to accommodate for the different functional group.